Okay, we are moving into a whole new part of calculus. Obviously, seniors, we only have 2.5 weeks left together. So we are going to just kind of have an introduction to this new part of calculus, and that's called integral calculus. So, those of you who are taking calculus next year or beyond as part of your college studies, generally the first semester of a college calculus course will focus in on derivatives. So that's what you've been doing up until now. And then the second semester of a calculus course is, so Calc 2, is integral calculus. And then some of you, if you're studying engineering or things like that, will move on beyond that. So you'll do all sorts of things. But the two basic tenets of calculus are working with derivatives and then working with what we're getting into right now. It's called integrals. So the whole big picture purpose when we're looking at derivatives, our focus is on slope. So derivatives allow us to find rates of change, and we can use those rates in many ways. So hopefully you have some sense of that. When you move into some of your calculus-based courses in college, you'll get an even better sense of that. The integral answers a different question. So I'm actually going to use a derivative to kind of show you why we need an integral. And I'm going to use a physics problem because that's what I'm comfortable with. So I'm going to use one of the most basic ones. That way, if you've not had physics before, you can still picture it. And so we're going to talk about velocity, or you could think of it as speed if you want. They are different. In physics, they're different. But right now, if you want to think about them interchangeably, that's fine. So I would say, using the notation of physics, I would say the average velocity of something is equal to its displacement. And we describe displacement in a physics course as x minus x naught. So change in position along a number line divided by time, right? This is a little bit of a more formal way. Again, for those of you who have had physics, obviously this has a vector. But in its simplest form, some of you saw speed as distance divided by time. This is the same idea, okay? So average velocity is something's displacement divided by time. Now, this allows me to figure out the speed, I guess, the rate at which something is moving, but I have to have a measurable distance and a measurable time. Calculus would allow me to find the instantaneous velocity. So if I said, I know I have a function for how something's moving. So an object is moving with, let's just say, a certain position time function. So 10t minus 16t squared. So this is how something's position is changing as a function of time. I could find the instantaneous velocity of this object by taking the derivative of this function. So velocity is equal to the derivative of position with respect to time. Now you've been seeing the Newtonian notation, so I've been trying to stick with that. And so, if I took the derivative, again, I'm doing nothing new here yet. This is totally review. The derivative would be 10 minus 32t. So I just took the first derivative, right? And this tells me the velocity of this object and how it's changing with time. Another way to write that is the Leibniz notation, and I'm just going to do that because we do see that a little bit more often. You're going to see it in the homework problems when we get into the antiderivative, so in the future. So dx dt is the exact same thing as the first derivative, so it would be 10 minus 32t, right? Okay, so again, this derivative is a powerful tool which is allowing me to find the velocity of this object at any moment in time. Graphically, if I realize my marker is done. Let me try a different one. These markers are fading. I think I might need an Amazon order for more supplies. There we go. Graphically, if I had a graph of time versus position. I'm not necessarily going to graph this one. I could. I'm not using actual values, but if I were to graph the position time function, finding the slope at any moment, right? The slope of this is change in position over time, change in time, which conceptually is the rate at which motion is occurring. So conceptually, the slope is the velocity of the graph, okay? So this is a whole long review, which may be helpful or may not be, for what the derivative tells us. Now, let's move forward. So derivatives are powerful ways of using slope, and we can apply them to all manner of physical situations. But sometimes it's not the slope of a curve we need. Sometimes it's the area under the curve that we need. And there's actually many, many, many uses for this second part of calculus, this integration. So I'm going to stick with this same physical idea using velocity. And let's say that I am given velocity, and I want to find the displacement after a certain period of time. So graphically, this could be a different kind of graph. This may be confusing to some of you, some of these graphs, and that's okay if it is. But I know I'm a very graph-driven person. I visualize things with graphs. So in case there are some of you like that, this may be helpful. If it's not, just keep on watching. I'll get to something easier. But if I have a graph and I have the velocity as a function of time. So for this particular equation, I just erased it, but I said the velocity is a function of time is the derivative of position. It was 10 minus 32t. Okay, so let's say I have velocity as a function of time. If it's a constant, if it's a straight line, so I mean in its easiest case, this is not a graph of this function. In its easiest case, it would just be like totally constant, right? I can find the displacement. Think about what this equation says, right? If velocity is displacement divided by time, velocity times time would give me my displacement. Again, I know I'm kind of getting physics heavy here, but everybody has heard the equation speed is distance divided by time. If I'm trying to find distance, speed times time would give me distance. You all did that somewhere in junior high. So it's the same idea here. Velocity times time would give me my displacement. And I can very easily find that, right? It would actually be the area under this quote curve. Clearly this is not a curve. Okay, so I take my velocity and multiply it by time, and I have my displacement. What happens if the velocity is changing? And what happens if the velocity is changing in a nonlinear way? Then we have a much more complicated situation. So let's say that, I'm not going to use numbers, but let's just visually describe it. Let's say I have a velocity that if I graphed it, looked something like, I don't even know, let's say I speed up and then I slow down. This is like what driving would be like, right? And I want to know up to this time right here, again, I'm not using actual numbers, what is my displacement? So just like before, the displacement is going to be the area under this curve. And that is very, very complicated to find. We don't know from geometry, there's no equation we have that would allow us to find the area for a shape like this one, right? We can do it, obviously, this is a rectangle. If this were a straight line, I'd have some kind of a triangle, probably. I can find those areas. This thing is complicated. I don't have the math right now to do that. And so this new sort of branch of calculus we're working our way into, integration, will allow us to do this. Now, we're not actually going to solve the area problems, so I just like kind of put it at the beginning of the PowerPoint. We're not actually going to solve the area problems and visualize it this way until the next section. So that's section 4.2, just FYI. But this is conceptually the powerful tool that integration can give us. So we would say differentiation, which is finding derivatives, that's what you've already done. That gives us the tool of slope, and we can use that finding rates of change in many, many ways. Integration, and I'm going to be using the word antiderivative to start out because that's what your textbook does. Integration and antiderivatives, they're the same thing. They're used interchangeably. That gives us this powerful tool of finding area, and that is an important thing. It also, we're not going to do it in the first year of calculus, but also finding volumes. I don't know if you've, when I do this with AP physics, so some of you have already heard it before, I talk about the volume of a donut. So that's like a really complex shape. Have you ever thought about the shape of a donut, like classic donut with the hole in the middle? How in the world would you find the volume of that thing? Like what is it actually? It's not a sphere, and then it's got this hollow thing. So calculus, integrative calculus, gives us the power to do that sort of thing. So anyways, that's the whole sort of conceptual overview. I would imagine if you're watching this and trying to follow, taking notes with me, I'm really just, I talked about the first 2 slides, that's all that I've done right now. You should think, I'm not sure that this makes sense yet. So if you're feeling that you're in the right spot. I've not really defined anything yet. So let's start to jump in, okay? So that's the big picture of chapter 4. And what I am going to do is just give you a few definitions, and in a separate video, just because this is getting long, we'll start to work through some problems. Now, my experience, strangely, I can picture in my head, like the integral is a little bit more tangible to me than the derivative, but I think most people's experiences are opposite that. So most math students would say that this is a little bit more confusing and difficult to work with than the derivative. So we're going to take it slowly. I would rather you at the end of this 2-week period have some idea and know how to do the basics of just integrating a function than have gotten through twice the material and be totally confused. So we're going to take it slowly. And you just sort of have to readjust yourself because we're doing everything we've been doing so far and we're going to reverse it. Okay? So the integral. The integral is the tool by which we can find those areas under curves. But what it really is the opposite of a derivative. So we call the integral, in this section we'll do it, we call it the antiderivative. I hope I spelled that right. Sometimes when I'm thinking and talking of derivative, yeah, I did. So we call it the antiderivative. So when I had my previous example, I had a function for displacement, right, for position, I should say. So I had a position function, whatever you want to call it. And I took the derivative of that. So this is where I have my little function x of t is equal to 10t minus 16t squared. Okay, so I took the derivative of that and I ended up with a velocity function. And again, we've done it just with formal plane functions. We've done it with functions for position. We did it with functions for area. We've done it for all manner of things. But I have a function, I took the derivative of it, and that gave me this new thing. And so what I was discussing was, what if I had this velocity function, and I wanted to find displacement? What I need to do is work backwards, right? So what I'm doing is I'm taking the antiderivative. So if I know my derivative, if this is known, instead of this, and I need to work backwards, I'm going to take the antiderivative to get back to my original function, right? So the antiderivative means we are given or known this thing, and we want to work back to our original function. That's the idea. So instead of being given my displacement or position function, I'll be given this thing, and then I ask you to find that. So if I am given the derivative, I want to find the original function, and that's the whole point of the antiderivative. So, sorry, I'm all over the place. Given the derivative, we want to find our original function. Again, how that links up with this whole area question that I had up before might not make sense yet. Give me 2 sections, so give me about a week and a half, and hopefully it will. So for now, we're just going to think, okay, how can we work our way backwards? That's the idea. Okay, so I want to run through the notation a little bit. And I'll really dive into it in the next video where I do the problems. Okay, so when I'm taking this, actually I shouldn't have erased this word. When I'm taking this antiderivative, we also call it the integral, we have a new symbol. So kind of looks like an S, not exactly. So this is the symbol for integration, or the integral as it's often called. And so I'm going to explain, I'm following along on the PowerPoint, so I use the same order, sorry, because sometimes I like to jump around. I need to explain the constant, which I will be doing later. So for now, if I have a function and I integrate it, so let's do the velocity function with respect to time, I would come out with my displacement function. Okay, so I don't know how, again, that probably doesn't make sense yet because I haven't explained it well, but I just want you to see this notation. I will, on the next video, really explain all of these terms, but this is just kind of what an integration problem looks like. So, like, I'm just talking size of letters. So this strange symbol is bigger, as you can tell, if you're going to write it neatly. I'm not that picky about things. The function you're going to integrate, so you would actually write the function in here. The function you're going to integrate comes first. The variable, I'll explain this more in the next one, but the variable you're going to integrate it with respect to is written next to it. Again, these are smaller than this thing, and then hopefully you would end up with your original function. So we'll stop here because I'm watching the time. These take forever to upload when I get over 15 minutes. And make sure you watch video 2 where I'm going to start to run through the problems and go through this process, okay?